Hello everybody. Today we are going to look at section 5.2, graphing polynomial functions. And so we're going to, throughout the lesson, look at different features of the equation and how that relates to different features on a graph. And so we're going to start with understanding the degree of a polynomial. So the degree of a polynomial is the highest power that you see. So typically we write a polynomial in decreasing powers of x. So for example, we might have something like 5x to the third minus 2x plus 6. And so we look for the highest power of x, which is x to the third power. And so that makes this a third degree polynomial. Okay? And so we're going to work on filling in this table to using the graphing calculator to get some attributes from our graphs. And so go ahead and take out your graphing calculator and graph y equals x and y equals x squared is the second one. So we'll do the first two together. Y equals x, you probably know what that looks like without using a graphing calculator. Y equals x is going to go through the origin and have a slope of 1. And so as we look at the domain, we need to understand domain is the x values and range is the y values that the graph covers. So if we take this graph and flatten it onto the x-axis, that would give us the domain. So in other words, if I flatten this graph onto the x-axis, it would go forever left to right. So that means the domain is all real numbers. We can say that x is anything in between negative infinity and infinity. Or if you wanted to use interval notation, you could write negative infinity, comma, infinity with the parentheses at the ends. Okay, and then for range, we're looking at the y values that the graph covers. And so imagine flattening this graph onto the y-axis. So if we pushed this way and this way to flatten the graph, it would end up on the y-axis, taking up the whole y-axis, going on forever. So the range is also all real numbers. So we'd say the y has to be, y can be anything in between negative infinity and infinity. And again, in interval notation, that would be negative infinity, comma, infinity. Okay, so as far as end behavior goes, end behavior is looking at the far extremes to the right and the left of this graph. So as we go further to the right, as x approaches infinity, we're going further to the right. This graph continues getting higher and higher and higher. So its y value is also going to infinity. So as x goes to infinity, y goes to infinity. Now we're going to look at the left end behavior. That's as x goes to negative infinity. So if we follow the left part of the graph, the further to the left that we go, as x goes toward negative infinity, further to the left, the y value is getting more and more negative. So we'd say the y value approaches negative infinity. So that's referred to end behavior because we're only talking about what's happening at the far extremes to the far right and far left of the graph. The second function, y equals x squared, if you graph that on your calculator, you'll see that that is just a parabola. You should already be familiar with that. So that's just a parabola that goes up on both ends. So again, if we imagine flattening that graph onto the x-axis, let me try that again. I'll draw it in a different color this time. If I take this red parabola and I want to find the domain, I'm going to flatten it onto the x-axis. So I'm going to take that graph and flatten it down onto the x-axis, and it would go forever to the left and right, covering the entire x-axis. So again, x, the domain is x can be anything from negative infinity to infinity. You can also think of it with this function. Are there any limitations to what you can plug in? And you can literally plug in any number you want for x and you'll be able to square it. So that's why the domain is any real number because you can plug in any number you want to this function and you'll be able to evaluate it. So in interval notation, again, negative infinity to infinity. Now for the range, here's where we're going to see a change. This time, we're going to take this red graph and smash it onto the y-axis. So if I smash that down onto the y-axis, remember where the arrows were. The arrows are up at the top, pointing upward. There's no arrow at the bottom, so when I smash this onto the x-axis, the arrows are still pointing up like this, so it's going to go up on the positive part of the y-axis forever, but it never goes down to the negative part, and so our range, our possible y values, start at 0 and go up to infinity. So that would look like this. In inequality notation, that would look like this. It goes from 0, or we could just simply say y is greater than or equal to 0. That would cover everything that we see. Y is greater than or equal to 0. So in interval notation, it would go from 0 to infinity. Now the end behavior, if we put our graph back the way that it was. Let me start over again. So I'll redraw that parabola. As x goes to infinity, that means we're going far to the right. Our graph's going up, 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 further up, and so the y value is also approaching infinity. And as we go to the left, it's also going up. And so both end behaviors are the same for this one. Both end behaviors are up. As the graph goes far to the right or far to the left, the graph goes up in the positive direction. So both of the ends are approaching positive infinity. Okay, so now I want you to go ahead and pause the video and try these 4 on your own with the graphing calculator to help. So go ahead and graph those 4 on a graphing calculator, complete all the empty blanks for the domain and range and for the end behavior. When you think you have everything right, then go ahead and press play and we'll see how you did. Okay, so from your graphing calculator, you should have found that the graph of x cubed looks like this. And so both the domain and range are all real numbers. It goes forever in the x direction and forever in the y direction. So both of these go from negative infinity to infinity for the domain and the range. Okay, the end behavior, as we go far to the right, it goes up toward positive infinity. As we go far to the left, it approaches negative infinity. X to the 4th looks very much the same as x squared. It goes up from the origin, goes up in both directions. So our domain is going to be negative infinity to infinity again, but our range is just positive x values greater than or equal to 0. And it's going up on both ends, infinity and infinity. And then x to the 5th is very similar to x cubed. It's going to have all real numbers for the domain and the range. It goes toward positive infinity to the right and negative infinity to the left. And then y equals x to the 6th. You'll see again looks very similar to x squared. It's just a little bit flatter on the bottom, but again, we can plug in any x value we want into this function. So this is going to be any real number, and the range again goes from 0 to infinity. So we should be noticing patterns in this table, and also both ends go up, so both end behaviors are toward positive infinity. So hopefully you notice some patterns in this table between the odd and the even powered functions, looking at all 6 of them. Notice that whenever the exponent is even, like when we have x squared, x to the 4th, x to the 6th, the end behaviors are both positive, or both the same. So these are the same on the ends, these are the same, these are the same. So the ends of an even graph always point in the same direction. Whereas for the odd-powered equations, like x cubed, x to the 5th, the ends go in opposite directions. One goes toward positive infinity, the other goes toward negative infinity. For x cubed, positive infinity, negative infinity, and for x to the 5th, positive infinity, negative infinity. So that means the ends of an odd-powered graph always go in opposite directions. And now go ahead and repeat that process for example B. These are the same 6 functions, except they have a negative sign in front. So I think you'll see after the first few that you graph on your calculator, you'll see some patterns right away, and how that compares to the problems that we just did. So go ahead and press pause, complete this part of the table using your graphing calculator for support, and then press play when you're ready to see the results. Okay, here are the results for all the negative graphs. These graphs are the same as the graphs we had on the other page, except they're flipped upside down because of the negative sign in front. So the first one, y equals negative x, still goes in opposite directions on both ends, but we see the end behavior is negative to the right and positive to the left. So that's the complete opposite of what we saw for negative x. For x squared, it's an even power. Negative x squared is an even power, so both ends do go in the same direction, but in this one, both of them are going down. So that's just an upside-down parabola, so that's not a surprise that both ends are going to go in the same direction. X cubed, negative x cubed, is just the opposite of x cubed, so the right end behavior is toward negative infinity, the left end behavior is toward positive infinity, and so on. So you can go ahead and compare your results with what this table shows. Press pause if you need more time there. And then we'll go ahead and move on to some more attributes of polynomial graphs. Okay, this time we're going to look at what happens when you have various factors to a polynomial, and if some of those factors are raised to a certain power. Okay, and so let's do x cubed together. And again, we can do this with graphing calculator support. So how many distinct factors does f of x have? There's only one factor, that is x, and it's repeated 3 times. And so there's one distinct factor, that is x. And what are the graph's x-intercepts? So when you, in order to make this function 0, x would need to equal 0. Is the graph tangent to the x-axis, or does it cross the x-axis? So we know that y equals x cubed, which looks like this, crosses the x-axis at its x-intercept. And so we'll say that it crosses. How many turning points does the graph have? This graph has 0 turning points. This one's, it'd be better if we had one that actually had turning points so you could see it, but we'll find out later. Turning points are where a graph changes from increasing to decreasing. So this would be considered a turning point, and this would be considered a turning point. This graph doesn't turn around anywhere. It's always climbing. And then The next part, how many global maximum values. This doesn't have any maximum values. It goes up forever and down forever. It has no global maximums or minimums. So this would be none, and this would also be none. Okay, and then let's graph the second function for the middle column, y equals x squared times x minus 2. Now here's a function that has some turning points, and so we see from the graph how many, or from the equation we can see that there are two distinct factors. That is, x is a factor and x minus 2 is a factor. So those are the two distinct factors. What are the graph's x-intercepts? So this graph would cross the x-axis, or where does it touch the x-axis? It touches at 0 and at 2 according to the graph. So x equals 0, x equals 2. Is the graph tangent to the x-axis, or does it cross the x-axis at each intercept? So at x equals 0, it just touches. It doesn't cross. So that is, we call that tangent at x equals 0, whereas at x equals 2, at x equals 2, we can see that it actually crosses the graph there, crosses the x-axis. Okay, how many turning points? 2. There's one at 0, 0, and one at approximately, it looks like about 1.2, negative 1.2. So 2 turning points. Okay, so we see the turning points again are here and here. That's where the graph turned around. It was climbing, then it turns around, now it's falling, then it turns around, now it's climbing again, so it turns twice. And then how many global maximum values? There are no global maximum values. There is no maximum to this graph because it goes up forever, it goes down forever, so again, there would be none. If we just had a parabola like this, that would be considered a global maximum. That is the single highest point on the graph. So that would be an example of what a global maximum would look like. We don't have a global maximum on this graph because there's no point that's higher than all the rest of them. Okay, so now go ahead and try to fill in the third column on your own. Graph that on your calculator and then see if you can fill in all the boxes. So press pause, fill in your boxes, and then after you're done filling those in, then go ahead and press play and see how you did. Okay, so what we want to recognize after doing these 3 examples is that when we have a factor that is raised to a power, like in this column here, we had an x squared. At that value, the curve was tangent to the graph. So what that means is, if we look over here at this graph, tangent to the graph means it just comes up and touches the axis. It doesn't cross the axis. So at x equals 0, it was tangent, and that's because that was a repeated factor. That was x squared. So whenever you have a factor raised to a power, an even power, it's going to be tangent to the axis, whereas if it's an odd power like first power or third power or fifth power, it's going to cross the axis. Okay, so we want to recognize that moving forward. And then notice that our total degree for all 3 of these is 3, because the first one is x cubed. The second one we have an x squared times an x, so that's 3rd degree. And then the third one is an x times an x times an x. That would also be 3rd degree. So all 3 of these are 3rd degree polynomials, and none of them have maxes or mins. So Let's now take a look at another example. Let's go to page 255, and we'll graph number 5 together. So this graph has an x squared, so that's a repeated factor. So we know that at x equals 0, it's just going to touch the axis. At x equals 4, from this factor, it's going to cross the axis. Our total degree for the problem is third degree because this is an x squared times an x. So it's a cubic function, which we know is going to finish in opposite directions. So it's either going to go down, down, or it's going to go up, down, up. And so since this one is negative, we know it's going to finish in the negative direction. So the sign of the polynomial, this is a negative polynomial. The negative sign tells us that it's going to finish going downward. And then we learned earlier today that it's if the polynomial is an odd degree, it's going to finish in opposite directions. And then since x is a even-powered factor, it's just going to bounce off the axis. It's not going to cross. It's going to be tangent to the axis. And then since x minus 4 is a odd degree, it's first power, it's going to cross. So there's an example of how we can graph just based on the factors of the polynomial. Okay, I'd like to do one more here, so if you can create some extra space on your booklet there, we're going to graph one more. We'll call this first one A, and for problem B, let's try one more just to see if you get the hang of it. This time we're going to graph y equals x minus 2 squared, and x plus 1 squared. Go ahead and try this one on your own, and then you can press play and I'll talk you through it and see how you did. So we can see from the equation in factored form that this factor indicates that x equals 0 would make the entire function 0. This factor indicates that x equals 2 would make the entire function 0. And this factor tells us that x equals -1 would make the entire function 0. So those are the zeros of the function. Those are the x-intercepts. So now we can draw our quick sketch. So we know that it's going to touch the axis at 0. It's going to touch the axis at +2. And it's going to touch the axis at -1. Now since the degree of this factor is 2, that means it's just going to bounce off the axis. This factor is also 2, or power is 2, so that's going to bounce as well. Whereas the x is just to the first power, so that's going to cross. So anytime we have an odd degree of a factor, it's going to cross the axis, whereas when we have an even degree, it's going to bounce off the axis. And since the total degree of this equation is 5, so it's 5th degree, I can tell that because this is x to the first power, this one is to the second power, and this one's to the second power, so if you add up the exponents, you get a 5th degree polynomial. So we know it's going to, that the end behavior is going to be opposite, so since our leading coefficient is positive, we know it's going to finish going up to the right. And since it's an odd degree, a 5th degree, it's going to finish in the opposite direction to the left. So up to the right and down to the left. And now, remember we said that it's going to bounce off the axis at x equals 2. So it's going to bounce back up. And then it's going to cross the axis at 0. And then it's going to bounce at 1. And so our function would look something like that. It's also worth mentioning that if we have a higher odd degree factor, such as if we had, let's say, g of x is equal to x plus 1 cubed times x minus 4, for example. The third degree indicates that since it's odd, it's going to cross the axis, but as the degree gets higher, it makes the function flatter as it crosses through that x-intercept. So for example, here we have a x-intercept at -1 and an x-intercept at 4. Since the third degree is a higher degree, it's going to be very flat when it crosses at 3. So it would look something like that, and then crosses again at 4. So we just want to exaggerate how flat the function is when it crosses through. We can see what that looks like on the graphing calculator as well. So if I put in x plus 1 to the third power and x minus 4, we see that it gets very flat right here at the x-intercept. I actually had this one upside down, so we should fix that. Since this is a positive degree, it should go up on both ends. So I have the whole thing flipped upside down. So that should go up. That should go up. It's going to cross very flat when it crosses at 3. So it's going to cross flat and then cross normal at x equals 4. And again, what that looked like on the calculator. If we change our window a little bit, we can see that. I'm just going to change my y min and y max to, maybe I'll try -30 and 30. And so again, we see how flat it is here where it crosses the x-axis. Okay, so next we're going to look at an example of using polynomial equations in applications. So for this example on page 255, we're making a box out of a flat piece of cardboard. And so if we start with a box that measures 9 by 5, we have to cut the corners off in order to fold this up so that it looks like a box like this when we're done. And so when we cut those corners off, we're cutting off x units from each end. So x there, and so what's left, since that side used to be 9 inches long, we cut x off of each end, so we've removed 2x now, so that length is 9, take away 2x. Similarly here, we've taken x off of each end. It used to have a length of 5 from edge to edge, but now since we cut x off of each end, that measurement would be 5 minus 2x. Okay, so how that translates to the box once it's folded up, we have this three-dimensional box now, and this edge is 9 minus 2x, this is 5 minus 2x, and then the height of the box would be x. And so now we can come up with an expression for volume. We know the volume of a box is just length times width times height, or the area of the base times the height. And so either way, we get 9 minus 2x times 5 minus 2x times the height x. So that gives us an expression for the volume. And what we're going to do here is we're trying to figure out what value of x maximizes the volume of the box. Find the value of x that maximizes the volume of the box. And so what we can do is graph this expression on our calculator and look for the high point. Okay, so if we graph y equals 9 minus 2x times 5 minus 2x times x. And I'll just start with zoom 6. And we'll probably have to adjust our y values. Okay, so we're looking for the high point of this function. And so we need to make our window a little bit bigger in the y direction. So I'm going to make my y max 50 and see if I can see the top. There it is. So we're looking for the peak. We're looking for this high point right here. The graph does get higher past 1, 2, 3, 4, 5, but notice that we can't have an x value. We shouldn't even consider x values bigger than 5 because this side only started with a length of 5. There's no way we can remove 5 from both ends if we only started with 5 to begin with. So that's why we're looking for this maximum, which appears to be around 1. And so we can find a maximum on our calculator by going to second calc, maximum. And then when it asks for left bound, we just want to move our cursor so it's a little bit to the left of the high point and press enter. And then a little bit to the right of the high point. Press enter. And then guess, we try to put our cursor as close as we can to the high point. Press enter. And it'll find that high point for us. So it tells us our maximum volume, that's the y value, is about 21.02, and that happens when x is 1.03. So we'd write max volume equals 21.03. That would be in cubic inches, inches cubed, and that happens when x equals, what did we say, 1.03. So this was actually 0.02, and this was x equals 1.03. Okay, so now I'm going to have you try a problem similar to that on page 257. Go ahead and read problem 7. Give that a try. Write an equation for the volume. Graph it on the calculator. See if you can use the maximum feature on the calculator to find the maximum possible volume. So go ahead and press pause, work out your problem, and then when you're all done, go ahead and press play and see if you got the right answer. Okay, so this box, when we cut the corners off and fold up the edges, will give us a box that measures 25 minus 2x, 13 minus 2x by x. And so the volume of that box would be 25 minus 2x times 13 minus 2x times x. And so now we graph that on the calculator. And so I've got typed in for y1, 13 minus 2x times 25 minus 2x times x. And then I graphed that on a window from 0 to 10 or negative 10 to 10 for x, and negative 10 to 450 for y. And we're able to see the high point there on the graph. So I did have to adjust my window a couple times to get that. And now we're looking for the maximum. So we go to second calc, maximum. the left bound, we want to move the cursor just a little bit to the left of the high point. Press enter. When it asks for right bound, we move a little bit to the right of the high point. Press enter. And then guess, we try to get as close to the high point as we can. Press enter. And it finds our maximum volume is about 402.2 when x is 2.72. Okay, so max volume is 402.2. That would be in cubic inches again when the x value is 2.72. So we're cutting 2.72 inches off of each corner. Okay, so that completes today's lesson. And if you need to, feel free to rewind and watch some of the parts again if you need a refresher on how to find the maximum using your graphing calculator.